Hey everybody, we're talking about a special thing that happens in the 2 by 2 matrix game. Um, the zero sum matrix game that's 2 by 2 with two active strategies. We can use this quick method called oddments. Now it's the same thing as equalized expectations, right? It's what we do. Equalized expectations, what we do when we have a 2 by 2 matrix game, two active strategies, or 3 by 3, we have three active strategies. When it reduces by dominance, perhaps, but not all the way to a pure strategy solution. But if it reduces to 2 by 2, we can use oddments, all right? And the oddments are actually just the absolute value differences of the outcomes in the rows or the outcomes in the columns, but we use those oddments to make the optimal strategy proportions. Okay, so we're going to start with an example, and as we go through the procedure, we'll need an example. Why? Well, it's not that difficult, right? We're taking the absolute for the oddment for rows, we're taking the absolute value difference of 7 minus 2, which is 5. And then we're taking the absolute value difference for rows B, and negative 1 minus 6 is, again, absolute value difference is 7. And then we can turn these oddments into the optimal strategy proportions, which are 7/12 and 5/12. Let's go through that to show you how it works, okay? So again, the oddments for rows A and rows B are just the absolute value difference of the outcomes. And it's important to remember to do the absolute value of the difference. And I just did it up above, but here we go. 7 minus 2 is 5, and the absolute value of negative 1 minus 6 is 7. Okay, and then what do we do? To create the proportions we need, right? What we're going to do, wait, I'm sorry, we're doing the absolute value differences of the columns now to get the column oddments, right? So we're doing 7 minus a minus 1, that's 8, and we're doing 2 minus 6. The absolute value of that is 4. So 8 and 4 are the Collins oddments, okay? And the optimal strategy proportions, we switch, okay? Notice, right, that the proportion for rows A is the numerator is the row B oddment over the sum of the oddments. And again, for the rows B proportion, the numerator is the rows A oddment. So there's a little bit of switching going on, right? Where the oddments, at least in terms of the numerators, they switch positions, okay? And there's a graphic that'll show that on the next slide, right? So we create the absolute value differences. Those are the oddments. But the rows A oddment is 5, but it goes with the rows B proportion. And the numerator 7 is in the rows A proportion, even though it's the rows B oddment, right? And what is the denominator? The denominator is the sum of the oddments, right? So again, if you just remember, there's this quick little swap that happens between the oddments and the numerators of the proportions, we're good to go. And the same thing's going to happen for Colin, right? So for Colin A, it's his B oddment, and the numerator for Colin B proportion is the Colin A oddment, okay? And again, the same graphic will work. We can show it right below the game, and the 8 and the 4 swap. Now I know that 4/12 is 1/3 and 8/12 is 2/3, but again, I'm showing the unreduced fractions to show how the oddments are being put together. The denominators, just as in the row case for the columns, the denominators, the sum of the oddments. The oddments numerators switch sides, right? The colon A oddment becomes the colon B proportion numerator. All right, so when we gather that together, and again, I reduce the fractions for Colin, roses don't reduce because they're 7/12 and 5/12. How do we calculate the value of the game? Well, again, we know Colin plays 1/3, 2/3. Well, okay, then that's 7 times a third. Let me put parentheses in it or something, right? Plus 2 times 2/3. And if you think about that, that's 7 times 1 plus 2 times 2, that's 11 over 3. So the value of this game is 11/3. Now, it should also be true that if we check another um, expected value, we should find the same thing. So let's do colon A, right? And rows place 7/12, so we have 49/12 minus 5/12. 49/12 minus 5/12 is 44/12, which is 11/3, right? That is the same value either way. And we will pick that up this way. And again, all four expected values should be the same. I do like running one for rows and one for column just to double check the math and make sure everything's good. 44/12, if you think about it, it does reduce to 11/3 if I divide the numerator and denominator by 4. Okay. Yeah, when I first saw 44/12, it took me a couple of seconds to make sure that was the same value. All right. So example game two, and just notice how easy the oddments are to calculate, right? So I have -3 minus 1, so the absolute value of -3 minus 1 is 4. The absolute value of 0 minus a minus 4 is also 4. Well, 4 and 4, that's just 1/2, 1/2. If the oddments are the same, right, it's just the oddment over the sum of the oddments. And 1/2, 1/2. What about here? I have a -3 minus 0. Sorry, that should just be a +3. And then 1 minus a minus 4, that's going to be, absolute value is going to be +5. And so then for Colin, we're going to have 5/8, 3/8, right? And for rows, we're going to have 1/2, 1/2. And if rows plays 1/2, 1/2, then you can see the game value is -3/2. All right, so getting rid of those marks and calculations, let's show this. And again, in the notebook, we can actually do this in terms of, we can use the game solver code. All right, so let's jump in to the notebook. All right. And and the first thing we're doing is we're putting in our initialization code and the game solver code. Now, one thing you can do is if you double click on the game solver mode, it it makes it small, okay, right? So if I double click on this blue part, sorry, click on, I guess. You don't have to double click. And what does it do? It just reduces it so you can see the first line, but nothing else. It's not a big deal as long as it's been executed, it's there. And then what happens? Well, it doesn't get in the way. I can see more of the notebook on my computer screen. And if I need to, I can just open it back up by clicking on the three dots here or here. I can open it up, but I don't need it. The game solver has been created. All right, and you can make whatever notes you deem fit. I did include, the graphics so you can see it. So a lot of the solution um, for example one is provided for us. And what did I do? All right, notice that we're creating the example game. All right. And I want you to notice how this goes, right? The code on the right-hand side of the equal sign, we do np.array. Okay. And all the functions open and close with parentheses. But it turns out that the array, to turn it into this matrix that we need, is a curly brackets around the whole thing, and then curly brackets for the top row and curly brackets for the second row. So when I want to do this game up here, you can barely see it at the top, right? The 7, 2, -1, 6. When I want to do that, right, it goes in 7, 2 and -1, 6, right? I just want to show you about that, how we're using those square brackets, right? The square brackets create a list for the rows, and then the whole thing is in square brackets to turn it into this matrix. And again, let me, first of all, not run the solver. Let me just show the example game. You don't have to do this, but you can see it creates this array exactly as we need to, to match the game matrix. All right. And then when I have the example game entered properly, I can run the code solver parentheses example game. And you can see exactly what we determined, right? That the value is 11 thirds. Rose's strategies. Now, this is a little awkward, but this is 7/12. This is 5/12. You can verify that with a calculator. Um, and Colin is 1/3, 2/3, right? So these optimal strategy mixtures, which are represented as vectors, those are true. The game solver has confirmed it, okay? And that's cool. Why? Because it allows us to practice and always have a solution that we need. Okay, and this is a little awkward. This where are Collins? Um, this is weird. Um, as if you can see, right, that there, I'm not getting separation despite having the H space, the backslash H space. So what that H space is supposed to do is supposed to provide 5 millimeters of spacing before and after the and that doesn't really seem to be working. So what I'm going to do is I'm going to get rid of it. I'm just going to put some spaces around the and in the text box. And spaces are text, so that will give me just a little bit of separation there. And that's purely cosmetic. You don't have to do that if you don't want. Now let's take a look at example 2. And again, if I want to create, let's call it E2 or X2, I don't know, X2 equals what? We're going to do np dot array. And again, the parentheses for the whole thing, I'm going to do this, oops, the square brackets, then square brackets, comma, square brackets, right? And the top row is -3, comma 1. And the bottom row is 0, comma, -4, right? And so I can use the game solver on this real quickly, though. Let's actually get the oddments. I'm going to switch to markdown here, right? And so my row oddments, um, again, I'll create a bulleted list starting with the dash there. So my row oddments are -3 minus 1, that's -4, but the absolute value. So my row oddments are 4 and 4. Okay, and my column oddments, same thing. Column oddments are 3 and, wait, 3 and 5. And again, you can see this is working out how we need it. And so what are we going to say now? We're going to say that the that rows is going to play this strategy mixture, which is vec r. And let's not do vec r. We don't, well, okay, let's call it vec r, but let's do a row vector instead of a column vector. Um, and so I'm going to do left, backslash left parentheses, backslash right parentheses. Why? Well, because they're fractions, right? So I'm going to do frac, comma, backslash frac. And they're both 1/2. I probably could have done a quick copy paste to make that quicker. And then I'm going to close this. Right, so rows plays 1/2, 1/2. And right, so colon, and I'm gonna copy paste. Why? Well, I have the basic LaTeX code that I need. Change that vector to C. What does Colin play? Well, remember, Colin will play 5/8, right? Because the oddments are switching places. The column B oddment goes in the column A um, proportion, and the column A oddment, wait, for the column A oddment 3 goes into the column B proportion. There we go. And and what's our value going to be? Well, again, I pointed out that we can use rows, or we can use, yeah, rows is proportions, right? If we're doing the expected value of column A, we have -3 plus 0 times whatever, that second strategy mixture is. So it makes it really easy to see that the value is 3/2, right? Because we're just using Rose's optimal strategy mixture and calculating based on column A, right? So we're looking at -3/2. I'm trying to decide where to put it in there. Okay, we can just keep going here. And then the value is negative 3/2. Cha-ching. And we're running into an issue, right, where if I don't put a space between the rows, it's not necessarily respecting the hard return there. But let's just check to see if we got it right. So we are going to do solver x2. Okay, and the game value is -1.5, which verifies what we had. And again, we might need to to check our 12ths. 12ths aren't um, fractions that we know really well, but you'll notice, I'm sorry, 5/12ths. I meant 5/8ths, which you can see is correct. So our Collin strategy is in fact 5/8ths, 3/8ths. Rose strategy is 1/2, 1/2. So we're verifying, right, that everything's good here. Same thing with example 3, right? We're going to have for rows, and by the way, you will start to do this pretty quickly. Let's do for rows A, let's just get the proportion. Okay, so for rows A, um, what are the oddments? The oddments are going to be 11, no, let's see, they're going to be 9 and 6. Okay, so 9 and 6, the denominator is 15. Okay, sorry, 15. But 9 is the rows A oddment, 6 is the rows B, so that fraction is going to be 6/15. And then for rows B, we can again copy paste. Why? Because it's almost the same, except now it's a 9/15. I do know these fractions reduce. So again, sometimes we can go straight to the um, strategy, right? So strategy, the optimal strategy proportions rather than writing down the oddments. So what are we doing here? We're doing 1 minus 11, that's 10, 10 minus 5. We still have a 15 in the denominator, right? But we have a 5/15 for column A, and that leaves a 10/15 for column B. And switching that to markdown, and you see the colors change and everything's good. We have it. Okay. So then what's the value of the game? All right. Um, and actually, let me reduce these fractions real quickly. So, um, and again, I can take that code and copy paste it in. And 6/15 reduces to, we're dividing by 3, so that's 2/5, right? And 9/15 dividing by 3, that reduces to 3/5. And 5/15, that's 1/3. 10/15, that's 2/3. Okay. And then the expected value, that's why I did it, right? If I have 1/3 and 2/3, right, I have 1 times 1/3 plus 10 times 2/3. That's 21/3. Oh, the value is 7. Okay, so at the moment, let me just put this in down here. Value is 7. All right, and we often write that as v equals 7. All right, Again, remember this is from Rose's perspective. The game massively favors Rose, but look at the outcomes. The outcomes are rather large. 10, 11, 5 are rather large positive numbers. This game is balanced towards Rose and away from Colin, right? Okay, and then how do we do this? We're going to do x3 to be our example, and we're going to do np.array, right? And I want the parentheses on the outside, then I want the square brackets for the outside, and then I want square brackets for the first row, square brackets for the second row. So this becomes 1 comma 10 for the first row and 11 comma 5 for the second row. All right, and then I type solver x3, close parentheses, cha-ching. And notice that we get game value of 7, which is what we had. Collins strategy 1/3, 2/3. We got it in the right order. Notice that we have Rose strategy 2/5, 3/5, and we got that in the right order. So I'm not saying that you'd never need to write down the oddments. Again, on a pencil and paper test, it was a lot of times really easy because the game matrix is sitting right there. So you can make the notes in a very similar way to how they're listed in the graphic, right? It's often pretty easy just to jot down the oddments, then jot down the fractions, jot down the oddments, jot down the fractions. Um, there's a little work to be done with the expected value to get the value of the game. Um, so again, I'm not saying to do every single step. There are ways to kind of consolidate this. I made the graphics and went slowly. Why? Because once you understand the process, you can shorten it. I wanted you to understand exactly what was going on before we started shortening it. And the next thing that I want to point out is we have additional practice. Okay. Now, do the same thing as we did up here. The additional practice, they are ones that work. Okay. I have created the practice problems. How? So that there's no reduction by dominance. There isn't a pure strategy solution. So I've chosen games that will have oddment solutions. And so therefore you can scroll down and you can work these in the same way we just worked examples 1 and 2. All right. So oddments turn out to be very quick and easy for the 2 by 2 case. And we like them, right? Why? Because in the past, my students have had a high degree of success on quiz and test questions about oddments. All right. So good luck learning that, and I'll be back later in the week with some quizzes for you guys to begin showing what we've covered so far this semester.